Swayam Prabha. Digital India. Educated India.
In this lecture, I will mainly focus on protein stability, one of the applications of using different bioinformatics tools as well as the parameters to understand the structure of a protein as well as function of the protein in terms of protein stability. In the previous class, we discussed about predicting the 3D structure of a protein from its amino acid sequence, because the amino acid sequence contains information regarding the 3D structure. So, we can utilize the information which you can obtain from the sequence to predict the 3D structures. So, we discussed about various methods to predict the 3D structures, and one of the major ones is the homology modeling. Homology modeling is based on the assumption that if two sequences share high identity or homology, then these sequences have similar 3D structures, right. So, if the sequence identity is more than 80% or 90%, right, you can obtain a reliably good model, right, which can be similar to the structures which can be obtained by experiments. So, what are the various steps used in homology modeling? Starting from the template and do the alignment corrections and backbone generation, loop modeling, side chain orientations and the optimization, right. Finally, we validate the structure, right, using the energy or the stereochemical properties. So, if a sequence cannot have indetectable identity with any of the structures deposited in PDB, in this case the knowledge based approach will fail and homology modeling may not give you reliable results. So, you can use the fold recognition, right, based on the probability of the residues which can be in contact or the physical chemical properties, or depending on the gaps we can be able to identify the folding type. Even if it is not possible, then you can try to use the ab initio methods. You can start from scratch, and this is based on the physical energetic calculations. So, you can get the structures for any protein sequences. CASP is the competition for the structural prediction algorithms, right. You can submit and then evaluate based on known 3D structures. When you go with the protein stability, right, what is the protein stability means? Right, when the protein is synthesized in ribosomes and then go to the folded state, it fold from the random coil conformation to stable steady structures. So, the steady structures are also important, right, to perform a function. For example, if you have a thread, if it is loosely loose thread, then it is wobbling on the air. So, you can go anywhere, right, you can see the kite. So, it will go wobbling anywhere. So, in this case it is difficult to perform a function. So, when if you have a kind of thread, then maybe it is stable, right, then gives some specific conformation. Likewise, in our day to day life, right, if we are stable, we are healthy, then we are able to perform the functions, right. It is very important for the proteins to have the stable conformation. So, if you look into this unfolded state, there is a kind of wobbling conformation. So, the major factor which are influenced by this conformation, it is entropy, depends upon the how many degrees of freedom this protein they have in the unfolded state. Then we go to the folded state, right, this 3D structure is maintained by different types of interactions. Specifically, you can say that electrostatic interactions, van der Waals interactions, hydrogen bonds, hydrophobic interactions, disulfide bonds and so on. The electrostatic van der Waals and these are uncovalent interactions, or you can say disulfide bonds is this kind of the bond between the two sulfur atoms in system. So, if you look into this contribution in the folded state and the unfolded state, the contribution is very high in terms of all the types of interactions, and if you look into the difference between the folded and unfolded state, it is very less, right, and the difference is about 5 to 25 kilocalorie per mole. So, why this marginal stability is important? Because in the living systems, right, certain proteins should be available in in specific quantities. If you produce more and more proteins and if there is not able to degrade, then the amount will be very high. So, it is easier to degrade any protein at any point of time. Second aspect is, it is also important to change the conformation when a specific protein is interacting with any ligands or other biological molecule. So, in this case they have to maintain a small difference in stability between the unfolded state as well as in the folded state, and the difference is normally in the range of 5 to 25 kilocalorie per mole. So, now here we discussed about different terms. One, we discussed about the enthalpy, that is the total energy of the system determined by different types of interactions. On the other hand, we discussed about the entropy, this is mainly the unfolded state of the system, and these two terms can be related using free energy, right, that will give you the between the folded and unfolded state, that is 5 to 25 kilocalorie per mole. Then we discuss what is entropy or what is enthalpy or what is free energy. If we talk about enthalpy, right, what is the definition for enthalpy? Right, you might have studied in your school classes, right. So, it's the amount of heat used or released in a system at a constant pressure. So, if you see the enthalpy, it can consist of two terms, one is the internal energy of the system plus the product of pressure and volume, that is a mechanical work. So, if you see the enthalpy, it can be obtained related with any reference point, right, not for the any specific point, right. So, in this case we can see the change in enthalpy, not the absolute enthalpy, you can change the enthalpy, there is delta H. This can see with respect to any reference point. This can be related as delta E plus P into delta V, right, because a change in volume and change in internal energy of the system. If delta H is positive, then what does it mean? It is endothermic reactions, it absorbs heat, because of this absorption of heat it gets cold, right, this environment gets cold. So, now it is negative, there is a heat releasing process, this you can see exothermic process, in this case the environment gets hot. So, I have a question. So, what is the change in enthalpy in any reaction if it releases 100 kilojoule of energy and the P delta V work is 10 kilojoule. Here what is the solution? We can see delta H, this is equal to delta E plus P in delta V. Delta E, which what is the sign for delta E? Because it is releases, so this is minus 100 plus 10 kilojoule, that is equal to minus 90 kilojoule, right. This is, we can get the enthalpy for any system. If we take internal energy, so internal energy represents all the energy contained in the material, for example, it is kinetic energy, or you can see intramolecular interactions like bond energy, electrostatic energies, van der Waals force and so on. So, at constant pressure and volume, so delta V equal to 0, in this case you can see delta H equal to delta E, right. This is the internal energy of the system, right. You can represent delta H as the internal energy of the system, that means different types of interactions. When you go to entropy, simply entropy means the disorderness or the randomness in the system. So, if you are comparing the ordered system and the disordered system, which one will have high entropy? Disordered system, right. The ordered system has low entropy and the disordered system has less entropy. For example, if you have solid state, it is ice, right, you can see then go into water and then into vapor. So, in the case of ice, what is more random or less disordered? It is less disordered, it is more ordered. So, in this case the entropy is less, right, and compared to the water, then it increases in water, and you can see water vapor, you can see it is mostly disordered, and also you can see the difference from the solid to liquid and liquid to gaseous state, it is very highly disordered from the liquid to gas state. So, now if we have the enthalpy and the entropy, right, and also along with this temperature, that we can explain the free energy, that is called Gibbs free energy. So, this free energy is spontaneous if there is a net input of energy. So, in this case, right, this it is a spontaneous one. So, you have Gibbs free energy, we can use a symbol delta G to define Gibbs free energy, because we use the word Gibbs because firstly discovered by the J.W. Gibbs. This is the reason why we call this as Gibbs free energy. So, we can combine the enthalpy, entropy, right, and temperature, right, using the equation delta G equal to delta H minus T in delta S. Why we call this free energy? Because it is the energy available to work with the expense of the entropy. So, this is why I call this is the entropy of the system, here this is the enthalpy of the system. So, we can see delta G is given as delta H minus T in delta S. If delta E is negative, In this case the process is spontaneous, we can do work, right, we do not need any extra energy required to carry out the work. If it is positive, then we need, it is non spontaneous, we need to give energy to do the work. This is the reason if you use this delta G, usually this is negative, right. In this case it can do the work spontaneously. So, how to interpret this delta H and T delta S to get the value of delta G? So, if you see the different types of interactions, you can see delta H, this enthalpy. So, mainly the changes in bonding energy, and you can see different types of non-covalent interactions like van der Waals energy, hydrophobic energy, hydrogen bonds and other charge interactions. When you look at the entropic term, you can see this is the arrangement of the solvents in counter ions, how they changes. For example, the rotational degrees of freedom, translational changes and so on. This will account for the entropy of the system. So, we have the enthalpy and we have the entropy, you can calculate free energy, right. That is the general definition for the free energy. If you talk about the proteins, when you discuss in terms of the stability in proteins, how we obtain this free energy, how to obtain this delta G, and how this delta G is related with contributions of different interactions. We can get the experimental data using different experiments on one hand. On the second hand, you can see this experimental delta G can be related with the other interactions like electrostatic, van der Waals and hydrogen bonding interactions. We will see how we obtain this information. On one hand, delta G you can obtain from the experiments, right. For example, circular dichroism or differential scanning calorimetry or fluorescence spectroscopy and so on, right. There are two different ways, either we denature with thermal by giving heat, or we can denature using the denaturant like the urea or guanidinium hydrogen chloride and so on. So, actually can get, this is one side. So, on the other hand, you can see get the delta G, you can calculate delta G from protein 3D structures, various interactions, and you can relate how far this can be related with each other. So, let us see first how we get the experimental free energy using any of these techniques. Right, here you can see the data for the fluorescence spectroscopy, so and urea denaturation. So, we add urea, right, you can see the different concentrations of urea, so here 1 to 9, and you can see how we get the fluorescence intensity. In this part, right, in the leftmost side, so here and see, so here this is the folded state, right, and slowly if you add the denaturant, it comes to slowly denature, and if you can see the denaturation this side, and finally this stage you can see is completely unfolded. So, in the folded state, if you see the intensity is 366, right, this is the called YF, this is equal to 366, and the unfolded state you can see this is YU equal to 51. Then using this graph for different concentration and the fluorescence intensity values, it is possible to derive the value for delta G at any point. So, for example, if you take this point, in this case Y equal to 256, right, 256, then what is the contribution for the folded state and what is the contribution from the unfolded state? If you take any point, then if you add up the contribution for a folded Y folded plus the contribution from unfolded, this equal to 1, right. Here in this case fully folded, here unfolded, and if you take any point, that is a fraction. In this case you can give the value as any point y, the fraction y you can give as, this is the fraction for the folded state and here is a fraction for the unfolded state, y equal to yf into ff plus yu into fu. Now, you compare these equations, equation number 1 and equation number 2, we can derive the values for fu and ff. For example, here ff plus fu equal to 1. So, ff equal to from this equation, right, ff equal to 1 minus fu. Now, you substitute this value, right, in this equation, you can calculate the value of fu, right, yf minus y divided by yf minus yu. Likewise, you can get the ff as y minus yu divided by yf minus yu, right. For if you take this number, right, ff equal to 1 minus fu. So, here this will become y equal to yf into 1 minus fu plus yu into fu, right. Then you combine together, right, the fu and ff, and you solve this equation, you will get fu as this equation. Now you can have the values YF equal to 366, right, here you can see the 366 and here Y unfolded equal to 51, and we take any point, for example we take this point, right, this point. So, in this case Y equal to 56. So, substitute these values in this equation, then F u equal to 0.35, because this is equal to YF is 366, unfolding is 51 and the midpoint you take 256. Then the FF, this is given as Y minus YU divided by YF minus YU, right, you will give the values of YU, YF, right, and will get that value, this 0.65. So, we have the unfolded state and the folded state fractions, we can convert this information into equilibrium constant, that is the K. K is given as FU minus FF. So, FU we calculate 0.35, FF we calculate as 0.65, right, we take the ratio, then it is 0.54. Then we take the logarithmic of this one, right, this is equal to minus 0.61, from that we can calculate delta G. So, this is minus RT logarithmic of this equilibrium constant. So, RT equal to 0.596 kilocalorie per mole at 300 degree Kelvin, ln K is minus 0.61. So, substitute this value here and delta G you can get 367 kilocalorie per mole. So, if you do the experiments at different concentration of urea, you get the fluorescent density values. This will give you the density at the folded state and the unfolded state and at the different states from the folded to unfolded state. From the intensity values of the folded state, unfolded state and at any point you can derive the equilibrium constant, and from the equilibrium constant you can calculate the free energy, right, experimentally you can get, right, for any protein, right, using the fluorescence spectroscopy. Likewise, you can do it with the circular dichroism as well as differential scanning calorimetry. So, this is based on denaturation. Likewise, you can use thermal denaturation. So, what is thermal denaturation?
We get heat.
Give heat, right. So, here you can see with respect to temperature versus heat capacity. So, in this case you can directly measure this transition temperature, because the amount of heat required to raise the temperature by 1 degree Celsius with respect to the 1 gram of substance without any change in the state, right, with no change in the phase you can calculate. So, if you see the increase in temperature and finally you get the transition temperature, right, where the protein started to melt, and you get delta Cp, because you have the Cp as unfolded state and Cp as the native state, and get the difference, right, you can get the difference, this will give you the delta Cp. Using the delta Cp and the transition temperature, you can calculate the unfolded delta G at any temperature. T is at any temperature, and you can get the other information from this graph, and you can get the delta G using thermal denaturation. So, we get the data for delta G with the denaturation and thermal denaturation, right, these are the experimental data. Now, the question is how we interpret this data using the contribution from different interaction energies. So, how to do this? So, as we discussed earlier, what is delta G? This is the free energy difference between folded state and unfolded state. So, you can see the folded state and you can see the unfolded state. So, what are the contributions of the folded state? This is mainly enthalpy of the system. So, different interactions. What are the interactions? GHY, hydrophobic free energy, EL electrostatic free energy, and HB is hydrogen bonding free energy, disulfide bonding free energy, and you can see van der Waals free energy. These are all due to this folded state. When we take the unfolded state, what is the major contribution? Entropy, right? We can see the entropy contribution. And if you compare the folded and unfolded state is not completely random. There may be some interactions are present which are available in the folded state. This is what we call as non-entropic term. For example, if you have some sort of hydrogen bonds which are present in the unfolded state, this is for this we use non-entropic term. Now, we see how we estimate all the interactions from protein 3D structures, right. Already we explained various parameters. What are various parameters we discussed using 3D structures? Surrounding hydrophobicity, different types of interactions, and the solvent accessibility and the contacts, right. We discussed all these aspects. So, we use some of this information to estimate different interactions which contribute to the folded state of the protein. So, first let us discuss about hydrophobic free energy. Can we directly measure the hydrophobic free energy? We cannot measure, right, this kind of imaginary force, right. So, we can get the partition coefficient, right, say relative solubility of either the water plus organic solvents. You can use the octanol, you can use ethanol, right, you can use the concentration to get the partition, right. So, you can see this non-polar to aqueous and the different concentration, and you can see the free energy. Positive gives for the hydrophobic and the negative gives this non-polar amino acids. So, if you say the positive free energy, so transfer is unfavorable. In this case, the solubility of non-polar is more. So, this gives the hydrophobic residues, and negative free energy in this case it is less for the non-polar and gives the hydrophilic residues. So, now if we have these amino acid residues, we have the values, but for the proteins we cannot directly measure the hydrophobic free energy. But if you look into these parameters that we discussed in the previous classes about solvent accessibility and hydrophobicity, what is the correlation? Negative correlation, it is inversely related, right. If it is highly accessible, then less hydrophobic, and if it is less accessible, this is buried, they are highly hydrophobic, right. You can use this information, right. Hydrophobicity we cannot measure directly, but accessibility can we calculate? Yes, if you have the structures, then we have different methods. What are the methods to compute solvent accessibility? XS and XS, right. You have the get area, right. There are several methods you can calculate. So, then we convert this solvent accessibility to calculate the hydrophobic free energy, right. I will show you how to do that. So, we know that accessibility is inversely proportional to hydrophobicity. So, we can write GHY hydrophobic free energy, which is proportional to delta ASA I. So, this proportionality we put this sigma I, these atomic solvation parameters, how different amino groups of atoms like carbon or hydrogen or nitrogen or the oxygen behaves in the environment of this protein environment. So, you can see different chemical groups, and if you see this is positive for the hydrophobic atoms and negative for the charged and polar atoms, right, because of the inversely proportional between the hydrophobicity as well as the accessible surface area. So, now how to get these numbers, right. If you have these atomic solvation parameters, and then we can calculate free energy, right. For example, if you have the atomic solvation parameters for the different types of atoms, here I use 5 different types of atoms, right. What are the different atoms in protein structures? C, nitrogen, oxygen, sulfur, and the nitrogen we have 2 different types, one is neutral and then is positive charge. Oxygen we have 2 types, neutral and negative charge. So, here the neutral nitrogen oxygen we combine together, right, N and O, and N plus, O minus and S, but we can use different classifications, right. You can use nitrogen oxygen separately and the carbon, main chain carbon and the side chain carbon separately, right, depending upon the connectivities, depending on the amino acids, we can use several classifications, right. For simplicity here we use 5 different classes. Okay, if this is known, and then we can calculate the hydrophobic free energy. This is the method initially proposed by Heisenberg in 1984, right, they published a paper in Nature. So, here A folded is the folded state accessibility, A unfolded is the unfolded state accessibility. So, can we have the unfolded state accessibility? Yes, because if you have the Gly conformation and they calculate different systems and say the average or say the maximum values, we can get unfolded state. Can we get the high folded state accessibility? You can get, if it is each atom. So, which algorithm can we use? DSSP? No, we cannot use DSSP because it gives you residue wise. NXS we can use, right, or get area you can use for each atoms. So, we have the value the folded state and we get the value of all unfolded state, and if this is known delta sigma I, you can calculate the hydrophobic free energy. It is very simple. Now, the question is how to get this delta sigma I, right. I show you the accessibility. So, accessibility criteria we know, rolling water molecule, you can see how far this accessible to the solvent, each atom accessible to solvent, right. Here this is a figure, you are familiar with this figure now, right. You can see these residues are in the interior and these residues are at the surface, and if you run the program you can get the values, right, either the residue wise accessibility or the atom wise accessibility. For calculating this hydrophobic free energy, which data is required, atom wise or residue wise? Atom wise. So, you can see different atoms, you can use these values to calculate the hydrophobic free energy. So, here this is the atom level accessibility. So, we can calculate for each residues and all atoms. So, this for the glycine, alanine, for all the 20 residues we can have the extended state accessibility, right, you can have the values, right. These are the 20 different amino acids, we have the data for all the atoms, this is fine, this is for the extended state. right. Now we have the folded state, then you can calculate, but the problem is how we get the delta sigma I, we need to calculate. Then how to get this delta sigma I? So we relate delta sigma I with respect to accessibility and the hydrophobicity. So here delta Gr represents the hydrophobicity scale. For example, you can take any hydrophobicity indices, right. We discussed various hydrophobicity indices, either you obtain from experiments, thermodynamic transfer experiments, or you can get from the computational methods. For example, surrounding hydrophobicity, right, you can use any value for delta Gr. So how many different amino acid residues? 20 residues. So for each amino acid residue, for example alanine, you can derive equation delta sigma I and Ai also we know, for each atoms we know. If you take alanine, you can use this hydrophobicity value. What is the value for alanine? 13.85. This 13.85, okay, this is the left hand side. We relate with this atomic solvation parameters. How many atoms in alanine? Right, 5 atoms, right, 4 main chain atom plus one side chain atom. So if you make it into different groups, right, for example if you see this alanine, right, alanine, so we can see that this is the data for alanine, right, y axis that is equal to 13.85, x axis this side, right, left hand side you can see that is a combination of different sigma I. So different atoms in glycine alanine, this is N, C alpha, C O and C beta, but here this come to C, right here, and you can see N and O together. So in this case you can see this N is 1.3, right, this 1.3 delta sigma N, and here is O, here there is 0.9 plus 0.9 delta sigma O plus for the C, right. So what is the C? Totally this is 2.9 and 2.9, oh sorry, this is not 0.9, this is O is 4.8, right, O is here 4.8, C is here, you can, this is 2.9 plus 0.9 plus 17.8, this is delta sigma C, right. You can write this equation, you can use this equation, right, y equal to a plus b1 x1 plus b2 x2 plus up to bn xn. Here this is y is the hydrophobicity, right, here this is y is the hydrophobicity, and delta sigma I is the this is the parameters where we need to identify this one, right, this is the b1 b2 all these things, right, and Ai is a solvent accessibility. So you need to calculate the coefficients B. So for the alanine we get this one, right. For the glycine, this is a glycine. So if we see this is the C, this is 14.9 delta sigma C, and 2.6 this is also C, right, 2.6 into C, and O is 7.3, right, 7.3 is here, so 7.3 O, and N is 2.6, 2.9 sigma N. What is the value for the glycine? So we get the values here, glycine equal to 13.34. So in this case it is equated to 13.34. Likewise you can do for all the 20 different amino acid residues. Here we take the glycine, for you have the data only for the delta sigma C and delta sigma N or O, it is only 2 variables, right, and get the equation. Likewise alanine you get the 2 variables. If you go with the aspartic acid, right, how many groups you have? Right, you can see the C and N and O we can combine together, and there is O minus. What is O minus?
Negatively charged.
The negative charge. You can see the aspartic acid, aspartic acid, right. So here if you see, right, you can see this OD1 and the OD2. This is 12.2, right, and 16.9, right. You can add up these two, so you get 29.1. So you get 20 different equations. So 20 equations, how many variables? 5 variables, right. So now we can this y axis, you can see the, this is the hydrophobicity values. So what is the dimension of this matrix? 20 into
5, 1.
Right, 20 into 1. So you have the 20 different values. for example alanine 13.35, aspartic acid we have 20 different amino acids, right. So, this you can write in terms of these are the what is this dimension
20 into 5.
20 into 5, right, because these are 20 amino acids and 5
5.
atomic solvation parameters, right. These are 20 amino acids and this 5 for the
Variables.
delta sigma I atomic solvation parameters. Okay, what is this the dimension of this matrix? 5 into 1, right, because this is for the 5 delta sigma I plus 1. So, in this case, right, if you have 5 equations and 5 variables, then easily you can solve it using principal of least squares, right. This is the equation, this is the hydrophobicity, and here these are 5 different types of atomic solvation parameters, this is the matrix which have these values. But here our case we have 20 equations and we have only 5 variables. In this case we use the principle of least squares to see that identify the numbers, right, the coefficients, so that the deviation is the minimum. So, you can see the deviation is the minimum of this y minus y bar the whole square. If you do like this, you can calculate the atomic solution parameters using this equation, x transpose into x, right, this inverse, and x transpose into y. If you do like this, finally you end up with the matrix 5 into 1. So, because it is 5 into 20 this matrix and inverse is 20 into 5, and you can do the transpose, that is again 5 into 20, right, and this transpose 20 into 1. When you get solve these matrices, finally you get the matrix 5 into 1. So, here you can get the delta sigma I parameters. So, if we do this, we can get the values for all these 5 parameters, and I show the number, this is the numbers we obtain for the 5 groups. For example, carbon 12.02 and nitrogen oxygen minus 5.86, N plus minus 9.46, O minus 34.98 and sulfur 13.51. It makes sense because if you see the hydrophobic groups, mainly carbon and sulfur, you can see the positive values, right, for the transfer into the protein environment, and for the polar residues and charged residues, that is minus. And if you compare the polar and the charged one have more negative, right, than the polar ones, that means these numbers are meaningful and they are reliable, right, you can calculate the energy. So, when you get the delta sigma I, right, now we can easily calculate GHY, because we know this, we know the AI folded, right, we know the AI unfolded. So, now I give data, right, for example, for a particular protein you run NXS and then you can get the folded set ASA. So, for example, if you take the glutamic acid, right, residue number 1. So, here you have the values of ASA for different atoms. For the same glutamic acid, you can get unfolded set accessibility, right, show it here, right. So, glutamic acid you can write here. So, you can see the glutamic acid, we have the unfolded set ASA. So, unfolded set ASA we have, folded set ASA we have, delta sigma I we have. So, we can calculate the hydrophobic free energy. So, how to calculate the hydrophobic free energy? Right, delta H, for example, if we take this one. So, for example, if we take the N and O, we can join together. So, in this case 41 minus unfolded set we will get from this figure, and then again for the O 25 minus, you can see the value from this one multiplied by what is the value for N and O, minus 5.86. Then plus go with all the carbons, okay, 1, 2, 3, 4, 5, 5 carbons, you get the difference in accessible surface area and multiplied by delta sigma of what is sigma of C. What is the value of sigma of C? This is equal to 12.02, right, this is 12.02 plus you can go for this y1 and y2. So, in this case the value is minus 34.98, right, minus 34.98, and you can see the delta ASA of C of O minus. So, we need the data from the folded states, and for all the 20 residues you have the data in the unfolded state, and for each atom type you get the difference and multiply it with the atomic solvation parameters. So, this is a folded state, unfolded state, multiply, then you will get the values. So, do it for all the residues and add up everything together, then you will get the value for the GHY, right, for all the atoms in a particular protein. So, easily you can calculate. So, if you have the 3D structures, you can calculate the hydrophobic free energy. Even you can use the PDB param, that is the server which calculates more than 50 structure based parameters. You can get the hydrophobic free energy, right, for any protein of known structure, right. It is easy. Now, you can calculate the hydrophobic free energy.